So to start with some announcements, which you can read yourself. There is another page. So look at Slack channel. That's where urgent information is spread. I don't know why it says EM stack on Python. Maybe it's a new session, maybe not. I don't know. They just showed me the slide in a second. And if we are running late with picture taking, we'll be running late with cocktails. They said bar will not open until the pictures are taken. So don't be late, please. And the last handwritten note is we have run out of some sizes of t-shirts, but we have more on Thursday. So they have $10 a pop in addition for your family, friends, and supporters. So you'll get more. So now we'll start with a plenary session that has 2 talks. The second one will be by me on observing strategy. The first one will be by our special guest, Jason. He is a member of our science collaborations, I believe 2 collaborations on stars and galaxies. He's expert both for stars and galaxies, famous for his work on white dwarfs. He's a Canadian astronomer who moved to the US. He got his PhD at University of British Columbia. He was until recently project scientist at Space Telescope Science Institute for JWST. And he was doing such a great job that now he's project scientist for all the missions at Space Telescope Science Institute. And in addition, he's also a member of WFIRST Science Definition Team. And that survey, that mission will have a major impact on science that we want to do with LSST. It will improve many things that we can do with LSST. And so Jason will tell us about what to expect from WFIRST. Jason, please.
So I've been involved in the LSST project since before the Decadal Survey as one of the contributors to the LSST science book, and I've been with the project in shaping some of the decisions that we've made for many years now. More recently, I've gotten involved in the WFIRST mission, and I think this is an incredible opportunity for us to think about the synergies between these 2 programs. And really just want to echo what Beth and Steve said yesterday about incredible opportunity that we're in astronomy right now, launching this era of next generation survey astronomy. And I think the biggest value that we're going to get from that is by thinking holistically about these 2 complementary science programs. So this talk is going to start with a 7 or 8 minute introduction about the WFIRST mission. I know many of you have heard about it before, but some people probably haven't. And then I'll spend about 15 minutes talking about the LSST science case and how the LSST science case can be improved by thinking about WFIRST synergies. And so I really want to show how WFIRST can help LSST instead of the other way around. And then I'll conclude by just talking about what we as a community can do to try and foster this connection and the next steps that we might want to take. And so just kind of spark hopefully a nice discussion about that. So WFIRST is the Wide Field Infrared Survey Telescope, and if I had to summarize it on one slide, I'd probably use something like this. So it really is a mission of superlatives. It's not talking about the science yet, but just talking about the different capabilities, order of magnitude capabilities that WFIRST offers over what we've been able to do so far in astronomy. Telescopes in general come in 2 varieties. You've got your telephoto lenses like the Hubble Space Telescope, Spitzer, and you've got your wide-angle lenses like Sloan and LSST. WFIRST is the first mission that combines the best of both of these worlds. It's a programmed telescope that will have Hubble light sensitivity, Hubble light resolution, but over a field of view that's 100 times bigger than Hubble. That allows us to build high-resolution maps of the universe in detail for the first time, solar system, Milky Way galaxy, nearby galaxies, and the distant cosmos. It's also the equivalent of big data astrophysics that LSST represents for ground-based astronomy, but for space-based astronomy. Another incredibly important reason to make sure that WFIRST is successful is that it represents this technology transfer. The mirror for WFIRST, the 2.5-meter optics, was donated by the Department of Defense and the National Reconnaissance Office to NASA. So it's an incredible opportunity of taking technology that was developed for a purpose and using it to advance science. And if we can set that precedent, it can be very rewarding to science in the future. And then WFIRST also has another instrument to advance state-of-the-art coronagraphy to achieve light suppression at a factor of 1 billion to 1. And sort of pave the foundation for finding life on another world by studying the light from Earth-like planets around the sun-like stars. Our guiding principle for WFIRST is the same as the guiding principle for LSST. That's the New Worlds, New Horizons Decadal Survey from 2010, sorry, where LSST was a top priority for ground-based astronomy. WFIRST is a top priority for space-based astronomy. And the committee recognized that there were multiple science ideas that all required a similar architecture, that is wide field, near-infrared, high-resolution imaging. One of these is the core pillar, the dark energy, and understanding the eventual fate of the universe. Another one is mapping the full distribution of planets around other stars. Kepler has given us great insights on the distribution of hot planets that are in close to their stars, but our census of cold planets in the outskirts of their solar systems is highly incomplete. WFIRST will fix this. To do surveys of the universe at near-infrared wavelengths at high resolution. And then this technology development to expand the New Worlds program and begin to take the next steps to image Earth-like planets directly. Current status of WFIRST, so we have the telescope, as I said. It was donated by the Department of Defense. These are some beautiful pictures of the telescope that were just cleared recently, so you can see the full Hubble-sized optics. Instruments are being developed. There's a science team that's shaping the requirements for the science case and the requirements for these instruments, and so this includes the wide field instrument, which is a 300 million pixel camera with 18 4K detectors. That's the camera that will offer 100 times the Hubble field of view at the same resolution, same sensitivity. And there's also this chronographic instrument that I mentioned that achieves starlight suppression at factors of 1 billion to 1, which is orders of magnitude better than the capabilities that we have today on ground-based telescopes, as well as what we'll have with JWST in the near future. You put this together, I think this telescope is really the best of two worlds, and those two worlds have been highly successful. It's a Hubble-sized mirror with a survey-sized camera. And so that sort of represents if you think about the science return from the Hubble Space Telescope and the science return from the Slow Digital Sky Survey, these are arguably two of the most successful scientific experiments that we've ever created, have user communities in the many thousands and scientific publications in the many thousands. And so WFIRST will offer a guest observer program where anybody in the world can write a proposal to use the telescope to do their science, cutting-edge science in that era. But it also will offer a guest investigator program similar to LSST, where we take surveys of the universe and users can come into an archive and interact with those survey data sets to advance astrophysics. So it's really the best of these two incredible worlds. Just to give you an example of how powerful this is, let me show you a little video. This is one of my favorite images from the Hubble Space Telescope. It's a view of the Andromeda spiral galaxy. And if you look towards the top right of this image, you can already see what happens when we explore faint luminosities with ground-based telescopes. We simply don't have the resolution to resolve individual stars, but Hubble is just getting started in this regime. With Hubble, we're actually able to see nearby galaxies as a collection of their individual constituent stars, and separate individual stars at the parsec scale. So you're seeing the separation between dots in this image is the same as the separation between the sun and the nearest star to the sun. And because all of these stars are at the same distance, we resolve a lot of degeneracies in interpreting their light to understand how stars make up galaxies. And so this image has been incredibly rewarding for understanding the processes of cluster formation, cluster dissolution, the makeup of the spiral disk of a large galaxy, studying the dust content. You can actually see sort of a red band stretching from the top left to the bottom right. That's a column of dust extinguishing the light from those stars. calibrating fundamental relations like the stellar initial mass function. This is an ideal environment to do this. The problem is the way that we actually constructed this image. So Hubble wasn't designed to do this, and so you can kind of see the footprint of the Hubble imaging camera on the outline of this image. And so we had to use 400 individual pointings from the Hubble Space Telescope to be able to take that image. And with WFIRST, we get the same resolution and same sensitivity in 2 images. And so the speed of this telescope to do Hubble quality science is incredible. Put another way, you could look at 100 nearby galaxies and survey, take images like this of them in the same amount of time that we did one with Hubble. Here are some of the capabilities of the telescope, just parameterized into 3 tables, the imaging capabilities, the spectroscopic capabilities, and the coronagraphy. I won't spend a lot of time talking about this, but I will highlight a couple things. So first, note the wavelength range. So WFIRST was initially designed to sort of survey 1 and 2 microns. We've added some capabilities to it by including filters that are blueward of that. The detectors weren't cutting off until about 500 nanometers. And so now we'll have a set of detectors that go contiguously from about 500 nanometers out to 2 microns. And so an appreciable part of the wavelength range of WFIRST will overlap LSST. But then also note the sensitivity of this telescope, because it's a space-based imager with a Hubble-sized mirror. In about 1 hour, we can reach 28 magnitude. Right? So the WFIRST sensitivity in 1 hour will be deeper than the LSST sensitivity in 10 years. Right? So if you're looking for a truth image, if you're looking for a very sensitive image of some small part of your LSST survey, this is the ideal telescope to get you that. We also have spectroscopy with a GRISM over the full field of view over 0.3 square degrees and an integral field unit, and of course there's the coronagraphy that I already mentioned. There are different survey implementations for WFIRST that are being considered. These are yet to be optimized, but they include a high latitude survey, which is going to be 2,000 square degrees, fully overlapping the LSST survey footprint. This will achieve 27th magnitude in 4 different filters. There's a galactic bulge survey, which is a high cadence survey of the Milky Way bulge designed to find exoplanets, these cold exoplanets. So that's going to be 2 square degrees with multiple seasons each year of the mission. There's going to be numerous deep field surveys, which I think we should really think of in the context of the LSST deep drilling fields. These are several square degree images going down to 28th and 29th magnitude at 0.1 arcsec resolution. That's a supernova. Another way to phrase that is a supernova program for WFIRST. There's this exoplanet imaging program for coronagraphy, and then as I already mentioned, there's guest observer and guest investigator programs where anyone in the community can do any other science that they want with this telescope to open peer review competitions. All of that said, WFIRST is a mission for the entire astronomical community. 100% of the WFIRST observing time is available. The specific implementation of these core surveys and the teams that are involved in them, there will be a call for proposals to shape that. The WFIRST science team, of which I'm a member, is going to be disbanded in 2021, and there will be another science working group to take the project into operations, and everybody is open to apply for that. And all WFIRST data, so anybody in the world can use WFIRST, and all WFIRST data will be non-proprietary and will be publicly available to the entire world, so there are no data leaks. We have several toolkits available if you want to start predicting performance of WFIRST for your favorite science program. And these has been largely developed by the 2 science operating centers that are working on the project, Space Telescope Science Institute where I work, as well as IPAC at Caltech in California. And so please visit those websites if you're interested in more quantitative estimates of the performance that WFIRST will give. Okay, so I'm going to move to the science part of the presentation now. There are many different ways to express LSST-WFIRST synergies. Frequently people use plots and graphs to show the sensitivity as a function of wavelength, showing that they're highly complementary, showing the survey areas that overlap. There are white papers that have been written on some of the science synergies, and then my favorite is probably this plot in the bottom right that shows the survey grasp as a function of sensitivity. And so this is just the area that the telescope can survey normalized by its resolution as a function of sensitivity. You can see that WFIRST and LSST stand out in the top right part of the diagram, which is sort of increasing information content, or basically better is to the top right. And so these 2 programs are orders of magnitude more powerful for these kinds of survey grasp programs than anything that we've had before. So let me walk through some of the LSST science cases and discuss ways that I think WFIRST can enhance the science. So first, something that I've been involved in a lot since before the Decadal Survey is stars in the Milky Way galaxy. WFIRST is an impressive suite, LSST is an impressive suite of science goals related to the Milky Way galaxy and looking at individual stars. So this includes understanding the structure of the Milky Way galaxy through wide field maps of both the disk and the halo. One of the things that we can do with LSST is construct 3D spatial and metallicity maps. We want to get a complete census of the solar neighborhood, which is highly incomplete right now. Will Clarkson's probably in the audience somewhere. There's incredibly exciting programs to study the structure of the galactic bulge and bar. LSST is going to be a treasure trove for finding rare events, novae, exotic stars. And then there are special lines of sight, such as the Magellanic Clouds and star clusters, where LSST is going to give us a complete census of these systems. So WFIRST can enhance all of this science. One of the reasons for that is that key guest observer sightlines observed with WFIRST can separate sources that are blended in the LSST data. WFIRST is going to operate at higher resolution than LSST, and so the higher quality your astrometry and your morphology is in separating sources, the deeper that you will go. And so WFIRST can aid in that. Also, when you look at star clusters or crowded environments, WFIRST is going to allow us to push LSST into the central regions of those environments where LSST starts to encounter some limits because of its pixel size and the resolution seen limited observations often has. So WFIRST essentially extends LSST into the crowded regimes. So to try and understand this, we've begun trying to gain an understanding of what the color magnitude relation and what the populations of stellar populations look like in the infrared baselines. This is a beautiful color magnitude diagram of the star cluster 47 Tuck, and we've been able to model this color magnitude diagram, and we're already starting to achieve sub-DB ages for old stellar populations using the infrared color magnitude diagram. So with WFIRST, we're going to be able to do this and have an increased sensitivity to find cool, faint stars versus LSST, and study things like the initial mass function near the hydrogen burning limit, where the hydrogen burning limit is, and also put stringent tests on multiple stellar population scenarios. This is all going to be aided by Gaia, which is going to give us great distances to all of these stellar populations. That's still our biggest uncertainty in exploring the true properties of the stellar population. I mentioned the Microlights survey, so this is really a bulge cadence survey. It's going to give us light curves and astroseismology of 1 billion red giants. To give you an example, that image that you see on the right there is 1,500 times smaller than what the bulge WFIRST image will yield. Look at the density of stars in that image. And so Kepler has shown us that this kind of seismology can be incredibly important for measuring the internal structure of all stars, independently measure stellar masses and stellar mass loss for stars at different points in their evolution. And also there are ideas for joint programs between LSST and WFIRST to complete this cadence and discover isolated black holes and neutron stars. So there's a lot of synergies with the high cadence observations from WFIRST over integrated with LSST. Another big goal from LSST is to survey the disk of the Milky Way galaxy. There are many surveys that people are advocating to look into the planar regions of the Milky Way. One of the problems with that is that there's extinction. And so because WFIRST extends vision into the near infrared part of the spectrum, you can get through this extinction easier. So WFIRST will be able to build nice maps for LSST to follow in the planar regions. And also for deep surveys of the Magellanic Clouds, which is an important chapter in the LSST science book, WFIRST can give us the true luminosity function along certain sight lines in the Magellanic Clouds, or in fact even the whole thing with the Mosaic program, because it'll go deeper and it'll offer better star-galaxy separation than LSST does. Let me move on to the next science theme, which is the local volume, nearby galaxies. And I've actually lumped the galactic halo into this just because the science resonates a little bit better. This is going to be an incredible project on LSST to really test simulations of galaxy formation in exquisite detail. This is a near-field cosmology theme. We're going to be able to infer with LSST what the true census of dwarf galaxies is and the halos of large galaxies. We're going to be able to measure the accretion history and time tag those accretion history processes to infer star formation histories. We're going to map substructure to test those galaxy formation simulations. And really, these nearby galaxies represent this link between stars in the Milky Way and high redshift galaxies. These are the only systems in the nearby universe where we can both establish the overall context and study systems in detail. Galaxies that are too far away, that becomes difficult to do. WFIRST is going to enhance all of this science. And so WFIRST has this high latitude survey that's frequently referred to as the cosmology survey or the dark energy survey, but it really is just a high latitude survey. We're going to look at 2,000 square degrees down to 27 magnitude at 0.1 arcsecond resolution. So you're effectively surveying the halo of the Milky Way galaxy to exquisite depth. And so this near infrared imaging is going to improve LSST completeness, especially for low mass stars that are cool. And the WFIRST imaging will be the ultimate data set to test LSST star-galaxy separation and perhaps even calibrate how LSST does star-galaxy separation. Just to give you an example of this, this is a beautiful picture from the Sloan Digital Sky Survey of the field of streams. It shows that our halo of our Milky Way galaxy is just flooded with substructure on all scales. But Sloan is only able to detect the faintest substructure up to 1% of the Milky Way's volume. WFIRST is going to be orders of magnitude more sensitive, and we'll be able to look at the substructure through the full volume of the stellar halo of the Milky Way galaxy in that 2,000 square degree survey. WFIRST, normally with Sloan, you find dwarf galaxies, you find substructure, and then you move to a bigger telescope to measure their properties, to measure star formation histories. For WFIRST, that's not going to be needed. You're going to be able to measure the star formation histories directly through the WFIRST imaging. And so you get a huge gain in resolving faint stars from background galaxies, which is one of the big challenges that LSST will have in resolving the substructure. One of the exciting opportunities here is also to use that high resolution imaging to enhance the LSST morphology, to enhance LSST star-galaxy separation, and then begin combining those data sets so you have from UV to near-infrared pan-chromatic imaging across the color magnitude diagram. The wider that you make your wavelength baseline for the same stars, the more detailed properties you can infer for the stars. So this gives us improved ages, metallicities, completeness for substructure. The picture on the right here shows an example of what an image from WFIRST might look like. This is Messier 101, which is a galaxy at a distance of 7 megaparsecs. And I don't know if you can tell, but there's a little red rectangle in one of those white rectangles. That's the Hubble field of view. To resolve these stars, we really do need Hubble quality imaging in the central regions of these galaxies. And WFIRST is going to extend that over the whole galaxy instead of the current pencil beams that we have that don't really give us the context of the full picture. Of course, the true sizes of these galaxies are huge. This is a picture of the best picture that we have of a fully resolved galaxy's stellar halo. This is Andromeda. Just to give you a sense of scale, the halo of Andromeda is about the size of a Big Dipper on the night sky. And so if you really want to study the full extent of these galaxies, you absolutely need LSST. WFIRST can't do that for nearby galaxies. And so WFIRST is really this connection that allows us to extend the LSST surveys of the halos of these galaxies into their central regions where crowding becomes more important. And then finally, WFIRST astrometry is going to be a cross-check for LSST proper motion studies, which is another priority for LSST. There are 3 different types of astrometry science cases that we're looking at: direct reference, spatial scanning. Then you probably just saw a paper on AstroPage a few days ago by David Spergel and collaborators on modeling the diffraction spikes in WFIRST to set a frame of reference for doing astrometry. And so we're very excited about exploring kinematic structure in the galactic halo with WFIRST, measuring the accretion history through the motions of stars, and even resolving the internal dynamics of star clusters and dwarf galaxies. And this is very complementary to the LSST science case, especially the proper motion measurements. So you move on to galaxies. There was a paper submitted a few days ago to AstroPage by Brad Robertson on the galaxy science roadmap for LSST. Not going to read through all of this, but there are numerous questions at the forefront of galaxy formation and galaxy evolution that LSST is going to address. These are some of the biggest questions that face us today in this region. It turns out that Brant is also the PI of one of the WFIRST science teams looking at the extragalactic science case for WFIRST, and there are several different ways that WFIRST is going to enhance the LSST science. So first, again, if you look at this high latitude survey, which is being optimized for cosmology and dark energy measurements, just by virtue of doing that survey, the galaxy luminosity function is going to look incredible. So WFIRST is going to measure more than 10,000 redshift 8.5 galaxies just through that survey. So this isn't a survey to find high redshift galaxies. This is just something that you get for free from the cosmology program. And so there will be 100,000 redshift 8 galaxies. This is a plot of the cumulative number of galaxies as a function of redshift. The red line at the bottom is our current census, and then the green and the gray bands are 2 different realizations, 5 sigma and 10 sigma, for how many galaxies we'll get with WFIRST. And so remember, this survey will overlap the WFIRST footprint. So for 15% of the WFIRST area, you'll have this incredible sort of truth survey of what the galaxy luminosity function looks like. WFIRST imaging is at 0.1 arcseconds, the resolution. And so that's going to allow us to distinguish faint structures in these galaxies and the shapes of the galaxies. So this basically aids in the LSST morphology and LSST classification of galaxy types. WFIRST is also going to provide Hubble-like imaging for hundreds of gravitational clusters, which complements LSST's weak lensing measurements with strong lensing in the cores of these clusters. To give you an example of this, if you look at the picture on the right, the panel on the right is a Subaru image. That's about the size of a WFIRST field of view. It's about half a degree across. And the central part, the image that you see on the left, that's a Hubble image of the core of that cluster. This is a gravitational cluster. Each of the things that you see color-coded is a background galaxy that's been lensed by this cluster. With Hubble, we're able to explore the cores of these clusters where strong lensing occurs. With WFIRST, we'll be able to extend that and match it to the weak lensing regime all the way up to the periphery of these clusters. This is going to give us constraints on cosmic structure formation, central dark matter distribution within small scales, and also discovery of rare, emerging first-time clusters that can set some limits on dark matter properties. And so this is very exciting, and it's one of the core LSST science cases, but WFIRST makes it better by giving us higher resolution imaging in the cores of these clusters. The WFIRST near infrared colors are going to directly add to the colors that we measure with LSST. This is going to give us sort of panchromatic imaging of the galaxy properties to infer the nature of the stellar populations. WFIRST is also going to achieve spectroscopy over its full 2,000 square degree survey. And so that GRISM spectroscopy, one of the goals there is designed to chart the history and topology of reionization for redshift 7 to 10. And the WFIRST planning also includes multiple deep fields that are very synergistic with LSST's deep drilling fields. And so let me give you an example of that. So some of the key questions that Pat Robertson's group is thinking of exploring with WFIRST, these resonate very strongly with the ones that I just showed for LSST. Or how do cosmic environments influence galaxy evolution? What can rare objects tell us about galaxy formation? When was cosmic reionization by through this spectroscopic mapping? And how do galaxies and quasars contribute to cosmic reionization? And so we really feel that WFIRST is going to be the ultimate probe to address these questions. But this gets even better if we start thinking about synergies within the deep fields and deep drilling fields with LSST with the WFIRST deep fields. So for example, here's an example of what a 50 dither mosaic to improve depth and image quality for WFIRST might look like. In the top left there, that's the blue image. To achieve a mosaic deep field over this 0.3 square degrees. And the image that you see is a Hubble UDF relative to scale on that WFIRST image. And so using the dropout technique, we're going to be probing 100 times more area than the Hubble ultra deep field. Right? This has been one of the pillars of extragalactic astronomy. Now imagine something at the same sensitivity that's 100 times wider. It's going to probe more area than contiguous JWST surveys, and it's going to discover thousands of high redshift galaxies above redshift of 10. And so this is very complementary to the supernova surveys and the high latitude survey, which are looking at different kinds of galaxies. For example, the deep field will be more sensitive to faint galaxies that produce the bulk of the cosmic UV luminosity density, which is one of the goals from LSST. It's also going to be incredibly important for reviewing targets that we want to then follow up in detail with JWST. So some of the opportunities between LSST and WFIRST here are going to be by trying to overlap the WFIRST supernova programs, which are just deep fields. We call them supernova programs, but they're just deep imaging fields with the LSST deep drilling fields. And so I'll just point out one out of the three that the supernova teams are considering, which is the deep supernova field. And so just imagine this. This is 5 square degrees, multiple filters, down to 29th magnitude. Right, so this is several magnitudes deeper than LSST survey at 0.1 arcsecond resolution. And of course, there are highly synergistic programs for the supernova measurements themselves, where combined light curve fitting between LSST and WFIRST enhances the return. So this is just a plot from a paper by Rebecca Hansel that appeared on AstroPH earlier this year. Finally, cosmology. The science goals, these are the dark energy science case is a pillar of the LSST science program and the WFIRST science program. Here we're looking at taking data that's going to constrain weak lensing, use type 1a supernova to calibrate the distance ladder, investigate large-scale structure, achieve cluster counts, and achieve robust photometric redshifts for a large number of galaxies in the universe. This was a plot that I made, or a graph that I made a couple of years ago, trying to take the WFIRST cosmology roadmap and summarizing it on sort of one slide. And so WFIRST cosmology roadmap has 3 different pillars to it. There's a supernova program that I just mentioned that's designed to find thousands, a couple thousand supernovae out to a redshift of 1.7, which is looking at a region that LSST will not. But then there's also this high latitude survey, which is a spectroscopic component to measure galaxy redshifts, and an imaging component to do weak lensings. And so this is very complementary to the kinds of measurements that we're going to be making with LSST. And again here, I think WFIRST can enhance the LSST science case. One of the problems with the LSST survey, or the challenges I should say, is going to be the blending of galaxies. This is going to lead to biases in shear estimation as well as biases in the photo Z's. I'll give you an example of that just in a minute. And this is going to be worse in galaxy clusters over the field. The WFIRST near-infrared imaging can directly improve the completeness of photo Z's, and also the sharp likelihood peaks in WFIRST will improve some of the biases in the shear estimation. LSST can also benefit from WFIRST because WFIRST will reach the full 27th magnitude limit of LSST, which it achieves after 10 years, but WFIRST gets that right away. And so for a fraction of the LSST science footprint, you'll have depth and detail to calibrate and test some of the LSST measurements. And so as David Weinberg has said several times, that WFIRST is the ultimate dark energy experiment. It's the ultimate supernova cosmology experiment because of its precision, redshift range, and control of systematics. It's the best controlled weak lensing experiment, and it's going to give us the densest large-scale map of structure at redshift 1 or 2. And so per unit time, right, WFIRST is the most powerful supernova weak lensing and redshift 1 to 2 spectroscopic facility. And the reason that I say that is that we're only investing in a baseline strawman design 2 years into the WFIRST cosmology program. We're investing 6 years with Euclid into that program and 10 years with LSST. And so for the cosmologists in the audience, think about this strategically, right? There are opportunities to be flexible. There are opportunities with WFIRST to do the cosmology program in very different ways and try and optimize the LSST-WFIRST synergy. And those kinds of decisions are completely open, and we should encourage communication on that. So the summary of my talk is that WFIRST makes LSST better in several different respects. It allows us to achieve better completeness, especially for faint stars and cool stars. It gives us much better deep blending. So this is just an image in the middle here showing Hubble images on the left and Subaru Supreme Cam images, which are a good analog for what LSST will see. And you can see by centrally on the galaxies that you resolve in the higher resolution images, you can do much better photometry from the ground. And then also it gives us better photometric redshifts. This is a plot that I ripped off from Jelko showing, or actually I think it's from Melissa Graham. Jelko probably ripped off from Melissa. It shows photo Z's if you measure them just on the LSST baseline, and then the same thing, but you just add the WFIRST colors. And you get a much tighter distribution between the true redshift and the photometric redshift when you do this. And if you look at the 3 plots on the bottom, they just highlight the scatter, the bias, and the outliers. The blue line is the LSST only measurement, and the red line is if we combine LSST and WFIRST data, everything is much better behaved on photo Z's. So actually, let me come back to this because I think I have a couple minutes here. I was going to end with that to spark a discussion, but I did want to say that our connection between LSST and WFIRST is going to happen in an era where we're launching this other telescope, right? So imagine an LSST-sized telescope in space, right? So this is JWST, which is going to launch late next year, and it's going to be much more powerful than both of these facilities for certain types of measurements. And so on any sort of nexus of thinking of WFIRST, LSST, and JWST, these are our 3 big priorities for the 2020s. JWST excels in both image quality and depth over either one of these 2 facilities. And JWST offers a wide range of modes to follow up interesting LSST discoveries, and also at the same time, I think it'll shape new astrophysics in the next couple of years that LSST and WFIRST will have to adapt to. And so just as an example, there's multiple ways of doing spectroscopy on JWST. There are 5 different types of integral field units. There's a multi-object spectrograph. There's 6 different types of coronography that we're going to do on JWST, and there's very high resolution imaging extending from 700 nanometers all the way up to 20 microns. And anybody can use JWST as well. It's open access to the whole world, and it'll be operating for several years before LSST, so it has a head start. So as we think about aligning our priorities in the 2020s, it's incredibly important to also think about how JWST might change that astronomical landscape, and how we might want to use JWST as a complement to LSST and WFIRST. So let me just conclude by talking a little bit, and this is meant to spark the discussion part. What is the LSST-WFIRST connection, and how do we take the next steps? And so I came up with some ideas, but I'm very interested in your feedback. So overall, it seems to be good coordination on the dark energy side. I think those communities on LSST and WFIRST are working well together. But I think the other communities really need to engage one another. I think we need better attendance and crosstalk between these different communities at our respective meetings. So at WFIRST meetings, it would be great if LSST people showed up and gave talks, and vice versa. Thank you for accepting my presentation. We should consider a joint WFIRST LSST science conference. And then we should really focus on ideas that are going to drive actual decisions that are about to be made, right? I mean, we're going to select what the LSST mini surveys and additional deep drilling fields are going to be soon, right? And so taking advantage of the same kinds of decisions that are being made on WFIRST are very important. We have to decide where the placement of the high latitude survey is going to be. We know it's going to overlap the LSST footprint, but maybe there's something more that we can do to maximize science from that. We have to decide where to put these supernova deep fields for WFIRST. Again, that should be synced up with WFIRST deep drilling fields. If it's not, I think that's a huge mistake. There's a tri-agency working group between DOE, NSF, and NASA that's looking at supporting synergies between WFIRST and LSST that go beyond the respective funded efforts from the agency. I think we need more communication about what this group is doing, and people here, the scientists from the LSST and WFIRST teams, should be involved in some of those meetings. So I know they're talking about cadence coordination, coordinated data releases, they're talking about joint pixel processing, they're talking about simulations. And they're currently defining requirements and estimating the scope, and I think they've been approved to go through with phase 2 of the project. I certainly feel I need to wire myself better into that process, and I hope others do as well. I know the group at Princeton and others have been looking at simulations. We all agree that Subaru Hypersupreme Cam is a great analog for LSST over smaller fields. But tying that to Hubble wide field camera 3D infrared imaging can be powerful, because wide field camera 3D infrared imaging is the same sensitivity and same resolution and same filters as WFIRST. And so even though it's a much smaller field of view, for those regions where we've imaged astrophysical objects, both with Subaru Supreme Cam and Hubble with C3IR, we have that analog of WFIRST plus LSST in terms of the data. Archival investments, I think LSST has been a leader in this. LSST has funded a robust data management system and made investments into arXiv, and I'm sure NASA can leverage from that. Public outreach, I would say the exact opposite. I think NASA has the right prescription here, and the NSF can take a page from NASA. And then another one that Steve actually answered yesterday in a different way than I would have answered is sort of short-term priorities that we want to convey to the next decadal survey. This process is going to start next year, right? The call for white papers for the decadal survey is next summer. And so maybe, I like Steve's answer about thinking what we do with LSST after 10 years. But I also think we should be thinking of short-term needs that we as a community have between these two incredible survey programs that are aligning into the 2020s. And then finally, I'll just put up the names of the WFIRST Formulation Science Working Group to help foster some of that communication. So if you know people on this list, or even if you don't, if you have ideas that resonate with some of the science goals that I talked about, please get in touch with us. All right, thank you. Michael, try to repeat the question as well, Michael.
Okay. So you hinted at this in your last slide, but talk a little bit more about coordination of the cadence of LSST and WFIRST. You mentioned the United States supernova electrodes that they include points from both surveys. Just want you to expand a little bit more on what else might make sense in sort of overlapping time.
Right, so that's a good question. I really think that, sorry. So Michael asked about other opportunities to sync up the cadence in WFIRST measurements and LSST measurements. And so the supernova program is one example where the fields for the supernova studies have not yet been selected. And I think it's a great opportunity for the LSST community looking at supernovae and measuring light curves to work with Sol Perlmutter and Ryan Foley, the two PIs in the WFIRST supernova programs, to make sure that we're looking at the same fields at the same time. Another example is the high cadence observations that WFIRST is going to acquire on the galactic bulge. This is a program where there's going to be 72-day campaigns twice per year for several years, not quite twice per year. And you know, so in doing the microlights measurements, if you can sync up the LSST data and the WFIRST data, you can actually measure a parallax, which can allow discovery of neutron stars and black holes, and these concepts are actually described in the new Cadence white paper by the WFIRST team. And so I think that's another opportunity. The other one that I'll just mention is the guest observer program. You know, really anything that involves transient phenomenon from LSST and variability. There could be programs that you could think about on WFIRST that operate in sort of a high cadence mode, and you have scheduling constraints to sync up those observations. And so I think if you're interested in variability and transient phenomenon, and you think high resolution imaging simultaneous to your LSST data might be useful, then you can propose that as a guest observer program and get in touch with the Fort Worth Science Work Community. But I think it's really a question for the LSST community, because this community has talked about and thought about high cadence observations more than the WFIRST.
Yeah, hi. My name is Chris. I'm Walter from Duke University. I was curious. So I've read online about a mid-2020s launch. So I guess I have two questions. The first thing is, if we're thinking about coordinating, what is the real schedule, first of all? And then, you said that all time is available for proposals. So what does that mean in terms of designing surveys and planning for surveys? We plan for some survey with some sort of overlap with WFIRST. Can we do that with some sort of assurance that that's going to happen, or is it always up in the air? How do you do a sort of proposal-driven pointing versus survey science?
Okay, two great questions. I use the mic, so I won't repeat them. So yes, so the launch of WFIRST in the current baseline schedule is 2025, 2026, so it's the mid-2020s. And so LSST will already be underway for 3 years or so, 3-4 years at that time. But I think that's okay. There's the kind of depth that LSST is reaching will be comparable at that time to the kind of depth that we'll be getting from the high latitude survey when WFIRST launches. Regarding the surveys, there is a distinction between the surveys and the guest observer programs. The guest observer program will be selected in each year of the mission through a peer review competition. The surveys will be locked in before that, and so WFIRST is designed to study dark energy, so there will be some process through which community science teams are selected to shape that survey and then execute it. So I think there will be an opportunity to get involved in shaping those surveys well before WFIRST launches. And so that will be in the early 2020s when we form a new science will be. Any other questions?
I'm Nicola Paitara from the Observatory of Naples. I wanted to ask what kind of plans have you planning for large scale spectroscopical follow-up? Because these are great imaging, of course, but some stages will probably need some medium high resolution. So that's going to be a challenge, right?
Yep, so that's a good question. So WFIRST does have spectroscopic capabilities for wide field spectroscopy, but it's GRISM spectroscopy over the 2,000 square degrees. You can also use the GRISM for guest observer programs and other science programs. But of course, that's relatively low resolution and lower signal to noise spectroscopy. And so I think, I think everybody recognizes that we're in this era of wide field imaging surveys, and it's going to be important to have access to wide field spectroscopic capabilities. And this has been prioritized by many different advisory bodies, and I think we will see some tools coming online on smaller telescopes that are dedicated to LSST follow-up and dedicated to providing spectroscopy for WFIRST imaging. I just don't know what those are right now, but I think it's well recognized that that's a priority and something that we need to fix. Any other questions maybe I can ask? I mean, does anybody have any other ideas on how we can better coordinate LSST WFIRST communications, other things that we can do to try and enhance crosstalk between the communities?
Money, always money.
Money is one. Right, but I think some of this is not as hard as it might seem, right? Because we, as scientists, are going to be using both of these facilities, even though we might be, more involved in one of them right now. And so I think just be a scientist taking the time to acknowledge the capabilities of the other facility and try and get involved in the science planning and the working groups that are being formed could be very helpful. And then, of course, on the back end as well, people that are thinking about the data management, people that are thinking of archiving capabilities. It would be great to try to understand what the structure that the other group is trying to build and see if there are things that we've already solved on one of the programs. I think that's certainly true for some of the early investments that LSST has made into data management, helping the WFIRST side.
Pat Burkett, Stanford. So can you comment more on the joint pixel processing simulations in terms of what activities are already occurring, so either you or someone else?
Yeah, I don't know if Steve's here, but it would be great for Steve to answer this one, because again, that's one of the things that I've heard about. I know what's happening, but I really feel like I myself need to get more wired into that. I think there was a proposal, and there was agreement between representatives from NASA, NSF, and DOE that this is going to be important, and we need to fund efforts to jointly analyze the data sets for these programs. What I don't know is exactly what milestones they have, what the timing is, and where that work is right now. I talked to George Malou yesterday, and he told me that they've submitted a proposal to move that work into phase 2, which is to achieve some of the things listed there, but I don't know more than that. I think we might be getting an answer.
Well, I don't know much of an answer. It won't be that satisfying, but so I'm involved in this effort, and the current status is following the phase 1 proposal. There were certain set of milestones, set of objectives, and so what they did was we're now in the process. We've had a few meetings with the joint pixel processing. We've identified leads and co-leads, but we're still identifying people to contribute to the work. So this is something that you're interested in. It's not too late to get started. And this is very clear things focusing on algorithms for optimal joint pixel processing. There's also tasks focused on what computing infrastructure is needed. And there are other outstanding questions. What responsibility does each survey have towards this effort? Do they only need to maintain their data, or do they need to work it into common formats? This is still very early stages, and so I'd encourage anyone who's interested to really reach out.
And who do people reach out to if they're interested?
Oh, sorry, Will Dawson at Lawrence Livermore National Lab. So I think George is the best one. You can George Luke, or you can email me and I'll put you in contact with them.
Okay, and then the last thing that I'll just mention on that, this is not just WFIRST and LSST, but it's WFIRST Euclid and LSST, is that right?
That's right. That's right. And it's tri-agency, so you've got NSF, DOE, and NASA.
Great, thank you, Will.
And Robert's the LSST rep on that.
Robert Lupton? Oh, okay, great.
Robert for Princeton.
I wish he wasn't so quiet. Okay.
Let's thank Jason again. Well, I'm setting up Lucian has an announcement to make.
I'll just do this from here. Hi, everybody. I think you all heard yesterday during Victor's talk a little short announcement about the unconference. Some of you might be wondering what an unconference is. and how you can participate. So this session will be held tomorrow afternoon. It is a format where we decide on the fly what sessions we're going to have. So this is a great moment where if there's anything that you wish was on the conference agenda, some opportunity to give a short talk and have a discussion, a free-form discussion about just about anything related to LSST that you like. Past examples have been a long, productive discussion about the Cadence, Operation Simulator, whatever it happens to be. You can even do a tutorial on something that you'd like to share as far as operating the stack, or I think one of our data science fellows might be offering some tutorials on some of the material we've been covering. It really is up to you. The way that you participate is you'll notice that outside there's a big board that says Unconference and some post-it notes. You can put up an idea that you have for a session, something that you'd like to see happen. It could be something you want to run, or it could be something that you wish somebody else would participate in so that you could join in. It's non-binding, so if you ultimately decide you don't want to do that session, that's totally fine. But put up your ideas, and if you see something you're interested in, you could put a little vote in for it. This is not a vote that says whether the session will happen or not. It just helps us judge what room to put you in. And then if you're interested in participating and you maybe don't want to suggest a session, just show up and you'll see what kind of things can be possible at that time and what people are interested in participating in. But I really encourage you to join, especially if you've never attended a conference before. It's a really great way to have all those conversations that you didn't know you wanted to have.
Thank you, Lucian. Thank you, Jason, again for this inspiring talk. I hope nobody on LSST team is thinking about quitting LSST and going to work with other firms. You'll get the data. I'm going to go briefly through essentially a progress report on work regarding our simulated observing strategies, scheduler development, and cadence optimization on behalf of the LSST simulations and scheduler teams. I'll talk a little bit about past, about what we achieved over the last 12 months since the last audience meeting. I will report on some changes in the way we do things. We are now entering the last phase of construction with the scheduler and optimization of the observing strategy. We essentially more than doubled the resources, the FTEs that we have at our disposal for this work. So we are going to embark on some new directions, and then I'll try to summarize at a high level what they would be for the next 3 years. This talk is very similar, but not identical to the talk I gave recently to the chairs of science collaboration. There are a number of talks from past all-hands meetings over the last couple of years that are useful if you are interested in this topic. Here are the links, and this talk is available on the web. I will not repeat any of the information in those past talks, unless it's changed. I will give you updates. But you can go back to these presentations and learn more. In particular, this one to the SAC a year ago or so, a year and a half, summarizes some of the motivation for this work. Why is this hard work? Why cannot it be already done? What can and cannot be done with the system? And how we will do optimization for the remainder of construction. So if you're interested in this problem of observing strategy, go and peruse these older talks. Today I'm only giving a status update relative to those talks. So why do we need to modify our current baseline cadence? You could say, well, it looks fine, it looks like what we wanted to do, it does meet the science requirement, documents requirements. Why do you want to tamper with it? There are two reasons. One is that we cannot prove that it's optimal or not even nearly optimal. Indeed, there are some very concrete science examples where we know we can improve it and enable more science. The second reason why we need to continue development is that we need to finish during the construction period a flexible and powerful system that will allow us to change what we want to do if something happens with the system during operations, either if something breaks or maybe science priorities change or whatever. We need to be able to start to model, to simulate new strategies and then decide what's the best way to use the system. So we still have 3 years to complete this process. Examples of optimization that we've been doing, driven by science programs over the last few years, are summarized here. Those in red are still open, and we are working on it. We just started working on rolling cadence, and as I will tell you later, there will be call for new deep drilling fields and new cadences for them. So what happened since the last all hands meeting? We adopted new baseline cadence, still with V3 code. I'll talk a little bit more about V4 code, and we did some major cadence optimization. I'll show you some results. Minion 1016 is our current baseline cadence. Of course, it is more than likely that it will be changed in near future, but if you're doing simulations right now, that's what you should reference your work to. It's got about 2.5 million visits, and here are the fraction of time spent on this cadence. There is a nice movie made by Lynn Jones. You can go there, and there is Al-Az projection. You can see how it jumps around the sky, covering the sky. There are a number of interesting cadence proposals that were submitted through this web form given at the top of the page. These that are listed here are not attempted yet. We decided a year ago that we will wait for V4 version of the scheduler, a major rewrite of the code, and in particular a new sky brightness model developed by Peter Joachim that will have a major impact on the science ability of the simulation. So we didn't do that. We did finish NEO optimized transfer. NEO stands for near Earth object. That was driven by NASA decision-making process. So Lynn Jones and collaborators did a lot of work. A major paper about 40 pages was submitted to Icarus, and it's just about to go back and to AstroPH. And basically the part of work that has to do with NEOs is done for now. NASA has their own decision process. We told them everything we could, and now the ball is in their court. So now let me tell you briefly where we are now. So the new version of scheduler was released in February. We are still testing it. It was tested from the engineering point of view by the team who developed it, led by Francisco Delgado, including Microlights. Now we are having people test it from scientific point of view. Essentially, we are trying to see if we can understand differences between baseline cadence Minion 1016 produced with V3 and this completely new piece of code. We do not expect, of course, bitwise identical results, but we expect to understand all the statistical differences between the two, and we are still working on it. A number of problems were fixed with V4. There is a slide in the backup slides of this talk where you can find the detailed list. I will not go through it here. And we plan to continue development of the scheduler until about 2020. We have 3 more years. And at Confluence pages for the scheduler, we can find the plan. It will be slightly revised over the next few months, but you can get a flavor of what remains to be done by looking at the plan. We still have open questions for how to optimize certain aspects of science programs. For example, the coverage of galactic plane was a straw man made by Abisaha, I believe, perhaps in Camp 2. And that's a straw man. We never had a proper process of getting input from the community and optimize galactic plane. And there are other examples in our current baseline that we want to revisit. So, driven by the need to have community tell us what are the priorities in an organized fashion that will be easy to act on by the project team, we formed so-called LSST Observing Strategy community 2 years ago to write a white paper that will be posted to AstroPH, that will be a living document, that will be updated as we go towards the beginning of operations, and that will be the main communication vehicle. The project committed that we will take this as input, that the project scientist will be responsible to read it in detail, to synthesize and act on the results presented in that paper. With support from the Science Advisory Committee that is tasked with making what I like to call astropolitical decisions. Decisions where we cannot just write down an equation and solve it, but it's judgment call, scientific judgment call. That's what we have SAC for. So in order to make it easier on us to understand what the community wants, we produced 10 cadence questions that each section that was organized by science topics was supposed to answer, and then we went through these answers of the other 100 and synthesized conclusions that then we are now acting on. And the two main conclusions are, the high-level conclusions are that there are enough science drivers that we should undertake a serious investigation of the rolling cadence idea. This is an idea where instead of trying to cover the sky or a given field uniformly in time over 10 years, so if you take 1,000 observations of that field, they will be Poisson distributed over 10 years. You want to compress it, and so that you get something that looks like accordion. You have dense sampling, and the need is about 3 times denser than uniform sampling, and then you don't sample for a while. And for example, in case of supernovae, if you do factor of 3, then you would have factor of 3 fewer supernovae discovered by LSST. But the density of points on their light curves would be 3 times as high. And the scientific trade-off is, from the supernova science collaboration, that we don't need that many supernovae in particular to discover, but we do need better light curves. So we'll take a hit in the number of supernovae. We'll go perhaps from 2 million or 1 million to factor of 3 down. But light curves will be much better to understand what we're looking at. And then there is additional motivation from linking asteroid detections to get orbits that also would like rolling cadence idea. And then there are many examples of short timescale variability that would benefit from. So this is what we are going to do over the next half a year or a year. We will produce very detailed rolling cadence simulations. And then we also asked science collaborations to tell us about special programs. Again, I'll use galactic plane as an example. We asked, how should we cover galactic plane? Should we do it as we have now, a strawman that spends about 1/3 of the total time for the main survey on galactic plane? Or should we extend the main survey to be the same cadence in the galactic plane as Andy Gold argued in his paper? Or something third? And basically the answer was, we can't tell you. That we cannot compute this from first principles. You, the project, needs to take reasonable ideas, like these 2 that I just mentioned, and we need to produce simulated cadences that will vary ideas in the galactic plane. And then the community can run their science metrics and tell us how they compare to each other. So the first step is up to the project. Then the community will tell us what kind of science they would extract from each of the simulations if one day LSST would really execute such strategy. So that's the plan. And this white paper that had a major impact on the project and our organization and what we plan to do for the remainder of construction became live on AstroPH this morning, or maybe last night. And we all owe many thanks to Phil Marshall, who was the leader of that effort. There were about 100 people who worked hard, but it could not have happened if it were not for Phil Marshall. He organized everyone. He issued about 7 million issues on GitHub. And it's finally out. So let's say thank you. I think this white paper is as important as our science book that we produced just before the last Decadal Survey. So now we have guidance, and the paper speaks for the community. So, in part, as a result of these recommendations in this white paper, the project decided after JPM a few months ago to do major reorganization of this effort and re-energize this effort by adding more resources. So there are 3 new hires for the scheduler development. So that's the team that does software engineering that is producing the code. There is new leader, scheduler scientist Tiago Ribeiro, and 2 developers, Colin and Andrew. Francisco Delgado was the author of before and previous versions. He is now the head of all the software for the telescope and site team. So he will participate as consultant at the level of the other 20%. These 3 people listed here will do major software engineering. And then as essentially users of that piece of code, the team led by Lynn Jones, including also new postdoc Owen Bobber and Ken Cook and myself, will then talk to community, take their input, and then use OpSim to produce new simulations. So we have separation of the software engineering from astronomical and community-related work. We have clearly identified responsibility. Most importantly, we have new resources. So I expect that you will get much more results over the next 3 years than we used to get before, because we doubled, actually more than doubled resources available for this project. And so let me just now briefly tell you what shall we do, at least over the next year, and roughly speaking, until the end of construction. I'm trying to leave at least 15 minutes for questions. So as I said, the one big difference is that we separated teams and responsibilities. They are still going to work very closely with each other, but we know now exactly who is responsible for what. We also are prepared to change the requirements. We are planning to take input from community, so we cannot have this naive idea of we will write requirements document, then we'll give it to the software engineering team that will go away, come back with the finished product. It works in some contexts, definitely not in this one, because we still don't know what in the end we want to deliver. As a case in point, I'm not going to talk in detail about excellent work by two groups that are not directly associated with the scheduler team. There is a group at Princeton led by Lahi, and a group at Harvard led by Daniel Rothschild and Christoph. They produced some very interesting, different algorithms for optimizing cadence. And I believe we should be able to use that logic in our official scheduler. And so that is an example where we will want to change the requirements and implement those in. That is not official, we are thinking about it, but it's a good example of why we cannot just believe in that naive idea of I'll have requirements 3 years before commissioning and I'm done with requirements, now let me code up the stuff. Of course, it all needs to be well controlled and managed. So we will not have, as we used to in R&D, have random scientists coming to random team members of this effort and say, can you please tweak this, can you please change that? That will not work anymore. There will be change control process, and the input, there will be 4 to 5 different ways to provide your input. I'll summarize them in a few slides, but it will be organized, managed process. So we will have 3 logical phases for the cadence optimization program for the remainder of construction. First, we need to develop tools, and that will be Seattle team led by Lynn and Owen. We need to move our ability to analyze a few dozen simulations essentially by hand with the help of math to automated analysis of many hundreds of simulations. It's not a major undertaking, but it will take some months to complete. We will also have components that will focus on interactions with the community. And originally we planned 2 calls, one for deep drilling fields and one for mini surveys. Yesterday we presented this plan to the SAC, and informal feedback at the meeting was that it would be better to do this as a single call, and I anticipate that will be the official recommendation from the staff. Pardon me?
It will be.
Excellent. So we will move December 2017 deadline by a few months into the future in order to finish the part that pertains to mini surveys, and I would anticipate somewhere in February or March of 2018 we would issue the call both for DDFs and mini surveys. Then we will have about 2 years to implement all these ideas, to simulate hundreds, and I'm secretly hoping perhaps for 1,000 or 2,000 different ways to execute LSST. And then we will produce a serious document for the SAC that will summarize different options for deploying LSST driven by these white papers. It will be essentially a menu of options with quantitative information that we will give to the SAC, and SAC will make astropolitical decisions. I have 2 examples later. So, one example is, do we want to stick to 10% for non-main survey programs, or do we want to perhaps increase it to 20% and cut the main survey to 80%? There are many arguments, pro and con, and we'll have to answer this question in due time. For the community and the SSC, we also will need help with metrics. And I'll go quickly over these words. I want to show these examples where the project is unable to answer questions without the help of a political body like the SSC. A good example is a very nice paper by Andy Gold, where he summarizes what could be achieved scientifically if we extended the main survey strategy to galactic plane. That would increase the time, observing time, the fraction of observing time spent in the galactic plane from about 2-3% to 10%. And the question that you cannot answer mathematically is that science, new science that we will get in the galactic plane, worth additional of the other 10% of LSST observing time? And the current plan is that the SAC will make recommendations to the project what is the right way to do it. That will be more than just A or B option, of course, but that's an example. Or if you need to compare two science programs like supernovae and proper motion, and you can improve both by 10%, but not both of them at the same time. You have to choose one of them. Of course, this is not job for the project to decide, it's the SAC that represents the community. And then we also expect SAC to help us with prioritization of those experiments, because it's plausible that the scope for white papers will result in more ideas than we can possibly support with just 2.5 people working. So this is tabular summary of the plan. The red rectangles are compute heavy. That's the use of the code by the Seattle group, plus camp work. 2020 is when we give 6 months to ourselves to write that document for the SAC. And then the SAC will have about a year to form the survey strategy committee and come back to us with recommendations about what would be the best way to start the survey. And then formally the director needs to accept the recommendations. The final decision rests with the project director. How can you provide your input? So the SAC is a way to give input if it's strategic, high-level input. For more detailed input about cadence and what we should do, first we have white paper. You can engage in that group of people, those 100 people that produce the first version of white paper. It will be a living document. Then, if you want to just have two-way discussion and clarify some ambiguities that you might have, that you want to talk about, we will have a category on community.lsst.org. Actually, Bill Clarkson already framed 3 excellent questions yesterday, but I was too tired to answer. We had soccer this morning at 6 a.m. It was a great idea. Thank you, George. I feel like I'm 50 again. Then we have that web form that we made live in 2015. It was not heavily used, but it's still alive and we are looking at it. And finally, if you have any other question that would not fit in either of these, just send me an email and we'll find a way to do it. So I will stop here. This is summary of my main points. And I believe we have 16 minutes for Q&A session. Thank you.
Just comment, one of the things that you said briefly, the Cadence white paper does describe a variety of different metrics. There's always a concern that the space of metrics doesn't yet span all the interesting space of science that LSST will do. So this is just a call to everybody to make sure that the science that you care about is captured in the metrics that we eventually use. So that's where for all of us.
Right. We do have some astronomical expertise on the project, but of course we don't have all the expertise. And there are so many science programs where we look at them and we are clueless about what's going on. And then you read carefully what people said and you see, wow, this is fantastic science that we could have lost had that person not pointed out the metric that we should add to math, and now it's protected. If you want to protect some of your great ideas, the best way to do it is to make sure that metric that measures performance of the simulation to enable this idea is implemented in math in our standard suite of metrics.
how do we manage the impact of changes in cadence or observing strategies on algorithms and hardware that are required? Is that, do our current plans put bounds on the cadence we could attempt, or do we try to change the plans for those things based on the cadence that we set?
This is an excellent question. So, some aspects of this question have been frustrating for years. Again, I'll use galactic plane. We ask people, scientists, science collaborations to tell us how to optimize cadence in the galactic plane. They tell us, we can't tell you before you tell us how will DM algorithms perform in crowded fields. Then we ask DM, tell us how well will your algorithms do in crowded fields. And DM says, well, you have to tell us how you're going to cover galactic plane and to what depth you're going to go. And so we are slowly beginning to untie the knot. And formally, we have project science team where project scientists for data management sits, as well as the pipeline scientists from the platform. And of course, we have many informal directions. Just recently, Melissa Graham, part of DM system science team, was put in charge of looking at the impact of cadence on algorithms and other way around. So Melissa is now responsible for that part. And of course, then she will contact DM and community and science team in case of ambiguities.
So Jacques, I wanted to add one more thing, because also mentioned hardware in this question. And I think at this point in time, we have to consider the hardware performance at boundary conditions. We're not going to be changing significantly the hardware to accommodate new survey strategies at this point.
You can't make it bigger?
Sorry. And that's true. It's something I've, we talk about issues and call for the community for new deep drilling ideas. I think we have to also give them clear definitions of what the limitations are hardware-wise.
Absolutely. Steve Ritz and Martin Morphy already produced a document that is now going through the process of being stamped, and then it will be circulated to TST and then community, that describes what are the boundary conditions coming from the camera, like minimum exposure time, filter change mechanism, what it can do, it cannot do, and so on. So that will be part of the call for white papers.
Great. And I'm Chuck Claiborne, by the way.
I'm
Chuck Claiborne, by the way, of LSST.
So I'm Beth Wellman at LSST University of Arizona, and there's something that we've discussed over the last few years that I've been thinking about a lot over the last couple of days, and in particular given some of the feedback about the accessibility of connecting with LSST and giving feedback, is that there's been a pretty high barrier of entry to contribute metrics to the white paper, and I've heard that from a lot of community members. I mean, folks like Phil Marshall, Peter Yoakum, Lynn Jones have done an amazing job of making it as accessible as possible and offering tutorials and to help folks to build these metrics. And there will be sessions along those lines here as well. But it remains the case that there's sort of a lot of donated time and a really steep technical learning curve to write the metrics and to work with the map. So I think this is a longer term discussion that we really want to sort of face as we're preparing these calls for white papers, especially. But I'd love to hear your initial thoughts on, whether there is some space for us to lower that bar for entry to get the science feedback.
Yeah, I agree. It would be easier. I did complain to Len. I said, I tried to do metric myself, and I don't know if I'm just stupid or old or what, but I couldn't do it. It's too complicated. I said, couldn't you do it this way, Len? And then she explains why I was doubly stupid. We couldn't do it. So basically, the decision was to make code be able to do very complicated things we want to do with analysis. And we did not plan to have 100 people write metrics themselves. But now that we have operational map, and that we understand that we want to lower the barrier, we'll try to think about how could we do like light version where it will be easier to write some simple metric. If you want to do complicated things, there is no way around it. You have to learn how it was designed, and it's a very powerful piece of code. For simple things, I fully agree. I myself would love to implement some simple metrics, and I never learned very deeply how to do it in math. It is not trivial, and by design, it cannot be trivial if you wanted to do what it was doing for the last few years. Lynn, if you want to add something to it, and Peter as authors of math.
Hi, I'm Lynn. I don't know if I have much to add. We're very happy to work with people and try and talk you through how to some approaches on the metric. I think we don't have huge amounts of time budgeted to a super amount of working with people, but we certainly are currently part of the plan is to go through the survey strategy white paper and try and make sure that if there's not a metric that's coded up already, that we can write one. And if you can describe it to us, we are happy to work with you to try to turn it into actual code that we can run. I think that's within our roadmap, right?
There are people outside of the project who adopted math and they are producing metrics. But we fully agree, it's not something you can learn in 20 minutes. We had workshops, there are ways to learn to do it, but you need to budget a week to learn the skill.
It does help if you are already familiar with Python and already are familiar with sort of the idea of object-oriented code. Then I think your time to pick it up is much shorter. If you don't know those things already, unfortunately that does mean you have a bit more overhead this year. But it's certainly not possible.
Thanks. Mike?
So I think the spirit of this question is a political one rather than so much technical barriers and all this stuff. So at WAS, will the SAC be the public face, or will it be Beth and Steve, or you, or what? Who reaches out to the community to do that? I'm specifically thinking about this map as somehow I find myself using the ABT for JWST this week. And it has its own peculiarities, but it's also a very different experience of like, okay, I'm not planning a survey, I'm just trying to plan an observation. That's what astronomers are used to sort of thinking about. They're not used to planning surveys. So it's a responsibility to make sure we plan and do the right thing regardless of whether or not someone knows Python but has a great science idea. Is that a rest with the project? Is that a rest with operations? Is that a rest with SAC?
Well, ultimately, it's the project director who represents the project. Now, with all due respect to our beloved director, I would not put him in front of 1,000 people at WAS to explain how math works. So it depends what they are trying to convey. If it's about community having input to what LSST will do, then it's a job for the SSC. If it's an issue of communication, the person in charge is better. So it depends on the company. If it's something about observing strategy, I'm the responsible one that we don't do stupid things when we start a survey.
Can you say a few words about how conflicts are handled in mathematics? So let's say, is it that you've got the WFIRST field and that takes priority, and then you move down to like tier 2 metrics and then try to optimize those? Or is there a weighting scheme?
I believe you're asking a question about OPSIM.
Sorry, OPSIM, yes.
Okay.
But yeah, using, like if I construct a metric.
There are different ways of doing it. The one that is implemented in the official scheduler takes a bunch of fields that have a chance of being chosen as the highest ranking fields, and then computes not the metrics that we are using in math to assess scientific value of the survey, but rather much simpler quantities. For example, how many times was this field observed? And a few others. And that's used to rank the fields. And then the highest ranking field, and then you calculate slew time, which goes against you if it's very long slew. And then you rank the fields, you pick the one that is highest ranked. That's not the only way to do it, but that's what OPSIM does now. There is a completely different approach that I mentioned earlier. We have Princeton and Harvard groups working on it. One is deterministic. It's an old idea from 10 years ago. We used to call it marching army, but never implemented. And Daniel Rochelle implemented it. It's deterministic. There is no ranking. We say, I'm going to do this pattern on the sky. Come hell or high water. And the output looks very similar in many statistics as our official baseline cadence produced by the other algorithm, which is encouraging. LRT produced a totally different way of doing it, which is powerful because it's not together with Peter, they already implemented a version that is not married to one field of view size in the sky, like the official scheduler. It can work on an arbitrary angular scale in Hilbert space, and it's not married in time to the same algorithm. Essentially, after each field, you could change your logic, your priorities, because it provides a map of the sky, multiple maps that summarize your priorities. And so it's a very powerful way, it has very powerful, what I call proposal grammar, to express your ideas for the even most complex things that would be hard to express in the official scheduler. So there are different ways of doing it, there is no unique answer. I can point you later to a paper that describes in detail what the official scheduler is doing by Francisco and this. Yeah, there is a paper published.
Eric Bell, University of Washington. Hey, Joko, I just wanted to make a quick comment, sort of tying some of the comments about usability of math, things of that nature. I was one of the chapter editors for the transients white paper that just came out on the archive today. And so I have some experience of trying to motivate external scientists to contribute to this process. And I think we should commend certainly the SIMS team, Lynn, Peter, yourself, as well as Phil Marshall for guiding this sort of complicated process in the last couple of years. My own feeling is that it's not so much that math is hard to use, it's that it's been hard for sort of random scientists who are interested in LSST to know that that work is going to be rewarded. And so I'm very encouraged by sort of outline you've laid out here of the white paper process. I think that in my experience, it seems like astronomers are very happy to use very complicated and weird tools as long as they see that it's going to give them access to a scarce or valuable resource. I won't make comments about IRAP here, but you get the idea. So I think that while certainly anything we can do to improve usability of math is great, I think even better is to help scientists see how their information, how their feedback is going to be used in a concrete way to really influence the search strategy.
Thank you, Eric. That's encouraging to hear.
See people writing emails and simulations about math. I think one sort of backward trend is the work that we've done now of having hosted places where you can run software would be very helpful, especially if we integrate the EM software and simulation software together. Because most of what math, you can learn to use it, but you have to have the stack installed somewhere. And that's not a trivial thing for a lot of people to do. So that's got to be a giant, even aside from learning how to use it, that's a giant stack of people on the table. Now it's behind. So having an environment where people can log on, I've been working on the way now, but having the simulation stuff available there and not just the measure now, was one good way to do it.
I fully agree. We already have good interaction between OPSIM math teams and simulations team. Actually, math people are part of the simulations team, so we'll rely on your experience more to make it more user-friendly. And everyone else, of course, if you have specific ideas how the interface could be improved, we would be happy to listen. And it looks like it's 10:30. So last call for questions. If not, let's have a copy. First time, second time. Okay, copy time. Thank you.